Hello, how's it going? In this video we are finally going to get rid of those validation errors that we were getting, and we're going to do that by introducing some very simple synchronization. I'm not doing anything fancy here, I just want to get the thing functional. And with that in mind, you can see we're working on paper at the moment. Let's talk about how this whole thing's going to work. So, we've got a swap chain, which is a collection of images that we can render to. The first thing we're going to want to do is we're going to sort of do some work on the, well, actually, I'll get rid of this. Okay, so the basic tasks. Number one, acquire an image from the swap chain. Number two, where is this? Render to that image. And then number three, present that image to the screen, and so on and so on. Now, as you can see, this is quite a nice progression. It's very linear. Things are executed in the order that they are given. However, this is not really how Vulkan works. If Vulkan was just spicy OpenGL, then it would probably work this way. The purpose of OpenGL is to take an asynchronous device, the GPU, and make it look as if it's synchronous by doing a lot of things under the hood. But with an asynchronous device, when we submit work on the GPU, there's no guarantee that things are going to happen in the order that they are submitted. There's no guarantee that things are going to happen like one by one. It's just, it's really fair game, all of it. And in addition to that, even if stuff does start working magically, synchronously, we also have the CPU to worry about. So there was some sort of work dispatched on the CPU, some sort of dispatch call, and the dispatch call is typically, not always, but typically smaller than the workload that the GPU is performing. So of course I'm on the CPU, so my dispatch calls are going to be in nice sequential order, but because they are taking less time than the GPU calls, there's a pretty high chance that things are going to mess up. So I'm going to have a few sort of synchronization operations. One is something called a semaphore. In Vulkan, a semaphore is a GPU object that a lot of function calls can tie in. So when we acquire the image, we tell that image acquiring operation that it needs to signal some semaphore, call it S0. And then we tell the render operation that it can't proceed until that semaphore has been signaled. And this is forcing these operations to be sequential. And then likewise, we'll take another semaphore, call it S1, and say, well, the renderer, when it's done, it signals S1, and then the presentation operation waits on S1. Now, as you can see here, the CPU work just happens really fast. It's dispatching the above work. Then we sort of can run into a problem. So let's say we go and render the next frame. We acquire an image again. There's the possibility, for instance, that while this other stuff is happening, like somewhere here, the next image acquire happens. And then it goes ahead and it signals S0. You can see we're starting to run into trouble because this, well, in the simplest case, it's possible, for instance, that the same command buffer is being reused multiple times, which is a really big problem in Vulkan. It will throw errors at you and slow everything down really badly. So what I want to do is I want to force the operations to happen like strictly sequentially, or maybe not as badly as this. This is what happens if I wait for the graphics queue to idle after every render, but something like this. So the issue is that this acquire image, semantically it doesn't wait on anything. But what we can do is we have another operation, another synchronization structure called a fence. And the benefit of a fence is that we can wait on a fence on the CPU. So this can sort of force the next set of dispatches to happen at a point that we choose. And it just so turns out that we can get this render to actually signal both the semaphore and a fence upon its completion. And so we sort of, at the start of the next frame, we wait on that fence that we're signaling, and then we dispatch another round of work. And this sort of, in the most overlapped case possible, this will sort of perform like this, in this order, or something like this. And then the the use of command buffers is separated. It's nice and secure. Then, when we come to the end of the next render operation, the fence gets signaled again, and we can sort of lay things out like this. Like I said, my purpose here is just to get it secure. I'm not super concerned about performance. We can play around with things a little bit more later, but this is sort of the idea that I have in mind. So with this in mind, let's jump over and have a look at the code. Okay, so here we are in the code, and I've added a few things. For one thing, I've gone ahead and put in some logic just to do some simple timing, because it's nice to know, what performance we're doing. So this will just sort of indicate the frame rate. As a matter of fact, we can run this now and have a look at the frame rate. So there you go. As you can see, it's something ridiculous, but that's what I would expect. We're not doing any rendering at the moment. We can leave that for now. I will talk about that later. But, so as you can see, we've sort of created, some semaphores and some fences, and these are, I hope, pretty much lining up with the diagram. So we go ahead, we fetch an image, and at the point where we fetch the image, we then signal to say, hey, we've acquired an image from the SOP chain, we are good to go. Then we go and render, and then again, at the point of completion, we signal, hey, we've rendered, we're good to go. Then we present, and then at the start of the next frame, we wait for the previous render to have completed. That's the point of this render finished fence. Cool. So again, semaphores are for synchronization pretty much directly on the GPU, between GPU and GPU, and fences are for synchronization between the GPU and the CPU. Another way to put it is when I have a fence, when I set up a semaphore, I can throw that at the GPU and it waits internally, but there's not, as far as I know, there's not a good way on the CPU to wait on that fence. Wait on that semaphore, but we can with the fence. Anyway, so I'm botching my explanation. That's totally fine. Also here in the renderer section, I've got the synchronization stuff, but it's not super exciting. It's the creation of these semaphores and fences, they're so lightweight. The only thing which is really interesting is when we create the fence, by default we want that to be in the signaled state, because of course when we go to render our first frame, there's no operation that we're waiting on. So we want that to pass straight away. But let's get into the meat and potatoes, the drawing operations. So the first thing I'm going to do is I'm going to get my logical device and make it wait on my render finished fence. So we go wait for fences, just like that. And we've got a few of these. First up, we'll have the fence that we're waiting on, or fences, and that will be my render finished fence. And then we have this wait all. So what we can have is we can have a whole bunch of fences, and then we want to indicate whether we want to wait for all of them to be signaled or just one of them. In this case, it really doesn't matter because we only have one, so it's the same thing. Right, so then we have the timeout, which is in nanoseconds, I believe. But if we put in a a sentinel value, the maximum uint 64, that counts as nothing. No timeout. Cool. So what I will then do is I'll then reset that fence. So the fence is it's good to go. And again, we'll just put in that render finished fence. So what this is doing is this is setting it up so that this render finished fence can be signaled by the render operation. Otherwise, if we don't reset it, the validation layer will complain at us and say, hey, you told me that when I finish rendering this image, you want me to signal this fence, but this fence is already signaled. So what's going on there, buddy? It's probably indicating a problem, and it'll squawk anyway, and that's annoying. So the next thing we'll do is we'll set a request to acquire an image from the swap chain. So we're going to get a uint32, get the logical device, and say, hey, acquire next image. And by the way, there's this acquire next image and acquire next image 2. I looked this up. What's the difference between them? The difference is that acquire next image 2 can have next pointers to extend the thing. But otherwise, performance-wise, they should be the same. Anyway, so we're going to put in our swap chain and then our timeout. So again, we'll go 64. And then we've got a few things. You can see here we can signal a semaphore and also signal a fence. One of those. In this case, I'm just going to signal a semaphore. So I'm going to say, all right, it's the image acquired semaphore that I'm going to signal. Everything else should be fine. So again, if we look at the flow of operations, first thing is we wait for the previous render to occur. Now, just a note, that does not mean that we're waiting on the previous presentation. So the thing with acquiring images, presenting images, they are sort of queuing and querying a queue. So when we present an image, all we're doing is we're queuing that up internally in some data structure to be presented at some point in time. And when we acquire an image, all we're doing is grabbing an image. Maybe it's pending on the queue, maybe it's free, good to go, but we're just sending a request to get an image. But the big thing that we need to wait on is the graphic stuff. So anyway, I'll stop talking. So what I need to do is I'm going to submit some work on my graphics queue, and I'm going to need Vulkan submit info to populate. It's going to need to do a few things. Command buffer count. It's a standard pattern here where we have, the number of things and the things. So then we're going to have a pointer to the command buffers. And this will be if I get my frames and grab its command buffer. The next thing I'm going to have is the semaphore that I'm waiting on. So I'll get my wait semaphore count will be 1. Then we have the waiting semaphores, and in addition to that, we're also going to need to specify which stage we're going to wait on those semaphores at. So what was it? It was the image acquired semaphore, and then I'm going to need to describe the waiting stage. Okay, so I'm going to need to have an image to render to, and the way I'll express that is I'll use the color attachment output flag for my wait stage. Okay, excellent. So that's all the stuff that I'm waiting on. Then it's a case of what will I signal? So I'm going to signal one semaphore, and that will be my render finished semaphore. Cool. Okay. So you might be wondering, we've set that all up. how are we going to signal that render finished fence? Well, it turns out that although the submit info doesn't take a fence that we can signal, the submission actually does. So if we get a graphics queue and we say, all right, submit, I'm going to submit our description above, and then we have the option to put in a fence, and this will be signaled when this is done. So we'll put in our render finished fence. That should all be fine. Okay, so I'm talking to myself, so now we'll go set up our present information, and this will be pretty similar. We're going to present to one swap chain. Then we're going to need to give the image index of that swap chain, which is being queued up for presentation. And then we're going to specify the semaphore that which we are waiting on, which is the graphics stuff, the render semaphore. And as you can see here, unlike the graphics operation, we don't really have a destination, a wait mask. So with all of that done, we can then get the graphics queue and present. And as you can see here, we don't really have anything that we can signal. We just put in our present info. So let's give that a shot. Okay, as you can see, this is working. It's going okay. But we do have something strange. We've got some messages. I said we'd come back to this. So if we go up here, we have this image memory barrier synchronization stuff. Now, I said that I would talk about this later, and I will talk about it later, but I just wanted to take the opportunity to play around with this and show how to debug stuff, because, side note, if you're following along, I've made a slight change to the image stuff. Actually, I'm gonna put it back to how it was. If I go to the frame, sorry, I'm talking out loud to myself. This is a good exercise. So let me put some more errors back in, give this a go. And yeah, as you can see, we've got a whole bunch of things. And I'll go right back up to the top. So first thing, I've got image memory barriers, command pipeline barrier. Okay. So it says color attachment write bit is not supported by the stage mask. That's the fragment bit. So the really cool thing about these error messages that we get is I can actually copy this code, bring it in, and in 30 minutes when the specification loads, I'll see a detailed sort of bit of info on what I did wrong and how to fix it. Okay, cool. So again, I'll talk about this at a future point, I guess, but yeah, memory barriers, it says that everything has to be supported, and it gives me this table of supported access types. So what I was trying to do is I was looking at, what was it? Color attachment write. And it specifies here that color attachment write can only occur sort of at the color attachment output stage, pipeline stage. So with that info in mind, I can sort of take that back here and say, get the color attachment output and use that stage instead of what I had before. And now we can see if we run this, very satisfying. The number of errors goes down a little bit. Now onto that original error. So it says there's something called synchronization 2. I know what you're thinking. Synchronization and synchronization 2? Could we come up with something a little more descriptive? But anyway, that's the situation. So again, I can just take this error message, copy it over, stick that in. It says if the synchronization to feature is not enabled, then there's all this stuff. But what I really want to go is I want to look in here and say, hey, how do we enable synchronization to? So it says Vulkan KHR synchronization 2, and there's, okay, so, what a nightmare. I found this originally and I thought it was very clever, and now that I'm looking back on it, I just can't find it. But I had a look for it specifically, and this is another way this is a way that we can enable synchronization too. So we have this struct, and this struct has a whole bunch of things that we can request, and one of those is this synchronization to feature. So what I'm going to do is I'm going to go back to my device, right down here to where I'm creating the device, and I'm going to request this feature via the struct. So I'll go physical device Vulkan 1.3 features. And then I can specify, so I'll go set set synchronization to, I'll set that to true. Okay, cool. So I've got some struct which somewhere is saying, hey, I want this thing. And if we look at the chain of things, we have shader features. After that, we look at dynamic features. And then after that, I'll look at those 1.3 features. And this is my way of chaining everything together. So we can then give that a spin, and we can see that it's working. We've got no errors. Awesome. We can then, it's pretty good performance. We can then go and close that down. And yeah, no errors. Nice. So that's always a good sign. Stability first. That's what I say. Understand the concepts, get it stable. Okay, so that is it. Again, in this video, we had a look at just a super simple way of synchronizing our drawing operations to get things like not hacked, like working properly. Yeah, I hope you enjoyed it, and I will see you again soon. Bye.